Moving on with our discussion, we're going to be looking for a quantitative measure for the disorder in a system. So this disorder is going to be what's increasing when we have a system in which a process occurs which is irreversible and is spontaneous. So spontaneous meaning that it occurs without the input of energy from any external source. So we want whatever measure of disorder we have, which is going to be increasing during these spontaneous processes. We also want this quantitative measure to be a state function, so we don't want it to be a path function. It should depend only on the initial and final states, what the change was during a process. So let's take a look at our typical expressions that we get from the first law of thermodynamics and see what we can do. So in the differential form, our first law says that the infinitesimal change in energy is the sum of the inexact differential of heat plus the inexact differential of work. And we're going to say for both of these that we want these to be for some given reversible process. So using this, we can rearrange that the heat of this process is the change in internal energy minus the differential of the work. And why the heat? Well, you can think of heat and temperature and higher temperature and more heat of the molecules getting hotter and hotter, moving around faster and faster, and there being more and more disorder as we go to higher temperatures, as you increase more and more heat is input into the system. So we like the heat and what it's kind of qualitatively telling us about disorder, but there's going to be a problem that, remember, heat and work, those are both path functions, so we want to find a state function. So let's replace this for some reversible process that we have. Well, our energy is going to depend on two factors if we keep the number of particles constant. That's going to be temperature and volume. So we have the heat capacity times the change in volume times the change in temperature. The CV dt, constant volume heat capacity, times change in temperature. That gives us how much that energy is changing with temperature. And then the negative of the work, remember that the work, if we assume it's an ideal gas, and then that's minus P dV, and then the minus sign here gives us plus P dV. But we remember from our ideal gas law that PV equals nRT, so P equals nRT over V. So what we have is that P dV is going to equal nRT over V dV. So we're going to put in here for our negative work here, that's going to change that to a positive, and we have nRT over V dV. So the reason this isn't a state function is because in our expression here for volume, this isn't all just constants times the infinitesimal change in volume. The temperature is going to change with the volume as well. So this factor out here is not a constant. And this factor CV here, that's a function of temperature and temperature only. That's not a function of volume because it's a constant volume heat capacity. So this term's fine, but we really need to figure out a way to get rid of the temperature dependence in this term. So what we're going to do is we're just going to go ahead and divide both sides by temperature. So our infinitesimal for reversible heat over temperature is going to be CV over T dt. We've divided by T plus, and now we divide out this T here. So we have nR over V dV. So now we have an interesting thing which has happened here. So this here, it had a temperature dependence, which is a variable in our total differential. So this was an inexact differential. And dividing by T, now this term has things that only depend on temperature times the change in temperature, plus things that only depend on volume times the change in volume. So both of these have now become exact differentials. And this was an exact differential up here to begin with, and it remains so down there. Okay, so if these are both exact differentials there, then that means our total function here does not depend on path because these differentials are exact. So what we're going to have over here is actually going to be a state function. So this quantity over here is going to be a state function. It will depend only on the final and initial endpoints, what its changes during a process. So this quantity, this heat divided by temperature, this dq rev, the heat of a reversible process over temperature, that's what we're going to define ds to be. And this quantity S is what we're going to call entropy. So entropy is going to be a state function, and it's going to be this quantitative measure of the disorder of a system. So if a system goes from a less to a more disordered state, then the entropy will go up, and if it goes from a less to a more ordered state, the entropy will go down. So high order means low entropy, low order means high entropy. Okay, so some other things we might want to mention here. Notice that we had this dq rev here, which was a path function. Remember heat being a path function. Then we divided it by temperature and it became a state function. So this function here, 1 over temperature, that would be referred to as the integrating factor of the irreversible heat, because if you multiply the irreversible heat by this integrating factor, then it becomes a state function, which we're defining as the entropy. So because the entropy is a state function, that means if we have some complete cycle, so if you have this notation like this, the entropy of a closed path, something where you start and end at the same point, this would be the same as saying the integral from some initial conditions back to the same initial conditions again, integrating entropy along that path. And this is going to be 0, because entropy is going to be the same at the initial and final conditions, being a state function, and the entropy change for that process will be 0. So what we've got here, we're going to delve into in great more detail, but this entropy, again, will be our quantitative measure that we want for the disorder, and during spontaneous processes, this will go up and it will maximize its value.